this session we will discuss exercise 15.10. In this exercise we will discuss area under a curve. So the area of each shaded region, so we have to find the area of this shaded region. The function y is equal to x cube minus 6x square plus 9x, and we have to put a limit from 0 to 3. So here all the area is within a positive region. So let's solve. Secondly, we will solve this and other problem. So let's start this problem. So exercise 15.10, area under a curve. This area with a function fx dA by x from a to b. This the limit of x is, initial limit is x and the final limit is b. So here we have initial limit is 0 and the final limit is 3, and this part 1, question number 1, part A. So we have this y, fx is basically y is a function of x, so this is fx. So fx, in place of this we will write this x cube minus 6x square plus 9x here dx. So we will evaluate this. So this is x cube, x4 upon 4, 6x cube upon 3 plus 9x square divided by 2. So limit 0 to 3. On substituting the limit, we have obtained this result. Three power 4, 2, 3 power 3, 9, 3 power square upon 2. So on simplification we have obtained 6 3 by 4, 27 upon 4, or that is 6 3 by 4. So this is part A. Now we'll solve part C. Here we have the 1 to 3 and the function is y is equal to 3x plus 6 upon x square minus 5. So we'll write it here, and the limit is 1 to 3, and on placing values here and taking the integrals and substituting the limits, and on simplifications we have obtained this result. This E part, we have area this, so we will have a limit 0 to pi by 2. This is the shaded region, so we'll have 0 and pi by 2, 2 sin x plus 3 cos x is here. This is 2 and sin x is minus cos x, 3, and this cos x is basically sin x. So limits is 0 to pi by 2. On substituting these limits, we have obtained this. So pi by 2 here, initial first upper limits minus lower limits, and on simplification we have obtained this. And question number 2, we have this area in the bottom side. So this y is equal to x minus 2. So this is x minus 2. So we'll substitute this x minus 2. So we'll open it, x square minus 2x. So take the limits from 0 to 2. And this is x cube upon 3 minus 2x square upon 2, 0 to 2, the limits in this 2 will cancel this. So this is 2 power 3 upon 3 minus 2 power square minus the lower limits are 0. So on solving this we have this result. Since this area is always a positive value, so we'll have the magnitude of this value, which is 1 over 3. Similarly, for part C, we have this y is equal to 4 upon x plus 2. So we'll take this from 0 to 3. This limits is 0 to 3. In place of fx, this 4 upon x plus 2, and this is 4, and x plus 2 is a single value, so we'll take this as a log value ln x plus 2. So limits are 0 to 3. On substituting this limit, so we have this 4 ln 5 by 2. Similarly, the other questions. Now question number 3. We have this function. Here we have a shaded region here, and then we have a shaded region here from -2 to -1 to 1. So the function is y is equal to is a polynomial, y is equal to x plus 2 and x plus 1 and x minus 1. So this is a cubic polynomial. So y is equal to obtained as x cube plus 2x square minus x minus 2. So for the shaded region, we have to find the area from -2 to -1. So this area is the area 1, and this area is area 2. So from -2 to -1, we will evaluate it by substituting this value. We obtained results is this 5 upon 12, and for the second region, -1 to +1, we have this region, and on solving this, we have obtained this 8 upon 3. So area 1 plus area 2 is equal to the total area, which is 37 upon 12 or 1 over 12. So this is very important. This question is very important from examination point of view, because the mistake we usually cover is minus. We take the limits from -1 to +1. So from here to here, it will always give the wrong result, wrong answer. So because area is always in terms of magnitude, so we have to cover this area as well. So this is a separate area. So this area and plus this area, and area always comes in form of magnitude. So this is a positive area, and this is also a positive area, because the magnitude is always taken as a positive. This is the result is -8 upon 3, but the area is 8 upon 3. So we'll add it and we will get the result as this. Now we have this function y is equal to x square minus 4, and we have to find the area. And here we have two regions, one region and second region, from -2 to 0, -2 to 0, and then 0 to 2. So we'll have minus area 1, this is area 1, this is area 2. So we take this, and this is +4, and the area 2 from 0 to 2. We have obtained -4, which is +4, because area is always taken as a mod value. So 4 minus 4 is 8. So this is the answer. Now question number 5, we have y is equal to this, and we have to find the area for 0. So we will question number 5. So read the question number 5 first. Find the area enclosed by the curve this, the x-axis, and the line x is equal to 4 and x is equal to 9. So we have to start limits from x is equal to 4 to x is equal to 9 for this function. We have to draw this curve, and after drawing this curve we will take value limits from 4 to 9. So let's start this. So we have this function, so we'll place this function here. We'll take the limit minus to 4 to 9, and this is, on taking the integral we have obtained this result, and on substituting the limits from 4 to 9 we obtained this. This is a 1 marks question, so it's simple. Similarly, find the area of the region enclosed by the curve this. This is y is equal to 12 upon x square, the x-axis, and the lines x is equal to 1 and x is equal to 4. So we have to find the area of the region. This is, and the line x is equal to p divides the region in part A into 2 equal parts. Find the value of this p. So we have to find a limit where x is equal to 5 that divides this area into 2 parts. This question number 6 is very, very important. So we have y is equal to 12 upon x square and x is equal to 1 to 4. So we'll take the area 12 upon x square dx, taking integrals, and we have obtained this, and by taking the limits from 1 to 4 we have obtained this result. Now in the part B we take a limits from 1 to p, and that 1 to p will be the area is half of this one. So we'll take this limits and we have obtained this, and this region is half of this one, so we'll take this 9 upon 2 because of half parts. So and after that we will solve for value of p, and where we have obtained the p value is 8 upon 5, which is 1.6. So this is very, very important from examination point of view. So this question number 6 is important. Now question number 7, show that d by dx x e power x minus e power x is equal to x ex. Use your result from part A to evaluate the area of the shaded region, this region from 0 to 2. So we have this region, so we'll differentiate it first. So on differentiating this part and this part, so this is x e power x, and from this is basically uv, and then this one. So this will give the same result, and this is u and v. So on solving we have this. So this is proved. This part is easy. In the second part we have to evaluate the area from 0 to 2, and we have this x e power x dx, and this is x e power x minus e power x. Because on integrating this word we will obtain this result. So this part B is using this value. So when we integrate this part we will get this one. So that's why in place of this we have write this. This is very important. So on substituting the limits from 0 to 2 we have this 2e power 2 and this. So eventually we obtain this result. Question number 8. Let's solve question number 10. Show that d by dx x cos x is equal to cos x minus x sin x. And using this part A, we will evaluate the area of this shaded region. So now we'll solve this question number 10. So here we have d by dx x cos x is equal to cos x minus x sin x. So this is we are differentiating this part. So we're taking this left hand side, and from this left hand side we'll solve it. So this is u and this is v. So we have obtained this on solving. This is 1, this is minus sin x, result of this. So on taking left hand side we have obtained this right hand side. So this is proved. In the second part we have to evaluate this x sin x dx. So this is x sin x dx. Is basically cos x let's see. So we have to find this region. So this is basically this part, and this x sin x dx is basically on integrating. In place of this x sin x, we can write this x cos x minus x cos x, which is x sin x. So when we integrate this part, so we will get this cos x minus x sin x. So in place of x sin x, we can write this cos x minus x sin x, because this differentiation gives this result. So when we integrate this part, we will integrate this part. So this cos x would be sin x. So this sin x will appear here. So on integrating this x cos x minus this x sin x. So x sin x is basically this one. So on integrating this part, so we'll take the integrals here, because this dy by dx will come here, and on. So we'll integrate this. So it will appear x cos x. We'll integrate it here. So cos x will be sin x. And integrating this one, x sin x. So x sin x is appear as cos x integral this one, and minus this part. So in place of this, this can be placed. This is very, very important. Just see this, because here we have this dy by dx. So we'll take this by dx, and cos x will appear as the x sin x. So on placing the limit minus pi by 2 to pi, so this is cos x minus x sin x. This is the integral value. So this is x cos x. This is equivalent to x cos x. So x cos x is this one. Similarly, x sin x from pi by 2 to pi is written as cos x dx x cos x. Cos x minus x cos x. Cos x x cos x. So we'll have this limit pi by 2 to pi and pi by 2 to pi. I'm substituting this limit, so this is sin x and this is x cos x. Because this has been already solved, and we have to integrate this one. This is sin x and this is x cos x. Now substituting the limit, so we have obtained this result as pi by 1, pi minus 1. This is important. This question is very, very important. Let's repeat it. We have dy by dx x cos x is equal to this. So we have evaluated this. Now we have to find x sin x dx. So we have integrate this one and we have to solve. So for integration of this one, so we will obtain x sin x as this part, because this part will appear in terms of this one. So when we integrate this, we will get x cos x. So integrate this, I will get x cos x. Therefore, x sin x is appear as this integral part will shift to the other side. So this x cos x will appear on the other side. So or this part will change here or this part will appear here. So because this is negative, so on the other side it will be positive. So x sin x and this part will appear here, and this x sin x part integral will be on the other side. So on the other side this will be positive. So this is integral of this one cos dx. This is this, and this part will appear as a negative on the other side. On substituting this value, we have obtained this result. This is very, very important. This question is easy but a little bit tricky. So this usually appears in the final exam of O level or IGCSE